The basic principle of distillation is difference in boiling points of the components that are in this mixture. Let's say that I have a round bottom flask in which I will fill my mixture. Now, some of the molecules in this mixture belong to one kind of a compound, while the other molecules belong to some other molecule or some other compound. And definitely there is a difference in their boiling points. For example, in our ethyl acetate and butyl acetate case, ethyl acetate has a boiling point of around 77 degrees Celsius, while the butyl acetate has a boiling point of around 120, 125 degrees Celsius. So we can see a clear difference in their boiling points. A simple distillation can be done if the boiling point difference between the two compounds is about 50 degrees Celsius. So when we heat our solution, both of these materials being volatile will convert into their gaseous form. So in the vapor, we will see mostly ethyl acetate and some butyl acetate also. And we say that the vapor composition is different from the liquid composition. So it is dependent on its boiling point and hence its vapor pressure also. But unfortunately, the material that you will collect as your vapor pressure or vapor composition, this vapor composition, when you will collect this, you will have few molecules of other material as well, which is not a very favorable when you have a closed system and you have a mixture, your compound or the volatile molecules become vapors. They rise up because hot air always rises up, and it then condenses on the sides of the cooler parts where it condenses as droplets. Once these droplets condense, they fall back in the pot. So we see that there is evaporation and there is condensation. When you have multiple cycles of evaporation and condensation, we say this is a reflux. Now, why the definition of reflux is important for us? Usually, we will not have a system which is closed. We would always want our system to have space to expand. You don't want this round bottom flask to burst up. When you will collect from a simple distillation is a mixture. So how can we improve upon our distillation? This is where our second form of distillation, known as fractional distillation comes into play. When we have fractional distillation, the temperature difference can be about 10 degrees Celsius apart. When we call as fractional distillation, what we mean is we will be collecting several fractions within that system. So now if you look at my round bottom flask, I have a longer neck with small fractions right here. Why do I need these fractions? These fractions can be inbuilt or can be introduced from outside. For example, a copper wiring. These fractions which we have introduced or are pre-created in that apparatus itself are increasing the surface area where cooling can happen and your material can be collected. Looking back at our mixture, let's say, let's use different colors. Let's say I have blue as my ethyl acetate and red as my butyl acetate. In today's experiment also, we have about 66 or 67% of butyl acetate and 33% of ethyl acetate. But when you will start to heat up this solution, we will see that our ethyl acetate being lower in boiling point will be collected and evaporate after evaporation and condensation more than the butyl acetate. No doubt, butyl acetate will also be evaporating out, but not as much as the ethyl acetate, who has a lower boiling point and a higher vapor pressure. And so, when the liquid gets converted into gases or its vapor form, it is cooled at one of the first fraction areas. And this is the material that gets collected. Eventually, heat will reach this part of the apparatus. It will make this liquid mixture also evaporate out. And then we will see that we are still evaporating out our materials, but your butyl acetate amount would reduce. How much? Let's say at the first fraction, if we have collected 85% ethyl acetate, now there is a big probability that we have collected 90% ethyl acetate from this portion. So from this portion, from this liquid, when this evaporated and cooled at this area, you got more ethyl acetate. So now in this particular collection, you have 90% ethyl acetate and only 10% butyl acetate. When you will heat this liquid collection also, it will evaporate and condense at the next fraction, you will now collect even lesser amount of butyl acetate and more amount of ethyl acetate. So now in this collected fraction, you have about, let's say, 5% butyl acetate and 95% acetate, and so on and so forth. I'm just making these numbers up. When you have collected this fraction, when you heat this fraction, you will collect even more amount of ethyl acetate, an even smaller amount of butyl acetate. Now let's say that you have only 2% butyl acetate and 98% ethyl acetate. And heating this composition finally gives us only pure ethyl acetate. So what have we done in this part? You had your mixture, you heated it, you cooled it, and then you observed that this is a particular composition that I've had. You take the same composition, you heat it, you cool it, and then you observe that now you have a new composition of ethyl acetate. You again heat it or evaporate it, you cool it or condense it, and then obtain a different composition. Now you can see these graphs or plates are reducing in size. What is reducing is the temperature at which it is heating this mixture composition. And also it is indicative that we are leading towards our lower boiling component. This can be understood by this graph. Now in this particular graph, first you need to understand how we read this graph. So on our y-axis, we have what is known as the composition, percent composition. There are two parallel temperature lines. On this particular line, we have 100% ethyl acetate, and on this particular line, temperature axis, we have 100% butyl acetate. When we have 100% of something, automatically the other material becomes 0%. And so, paying attention to this, we are at a 33% ethyl acetate and 66% butyl acetate mark. We heat and evaporate our material. We reach the bubble point where the material starts to condense. At this point, we collect our liquid and take assessment of it. What is the composition of this material? And we see that this is the composition at this point. We now heat or evaporate this particular collected material again, cool it, and see the new composition that is collected for this new vapor. And as we see, this was our first plate, this was our second plate. You can see that there is an increase in ethyl acetate, or the lower boiling component. You collect this material, you evaporate it, you cool it, and you see the new composition, followed by evaporating, heating again, and you see there is increase in the purity of ethyl acetate. Evaporate, cool, observe the composition, evaporate, cool, observe the composition, and then finally you will get the pure material. So if you count, we used many of these evaporation and condensation. One plate is defined as one cycle of evaporation and condensation. Theoretical plate. So this is the difference between reflux and theoretical plates. When your number of theoretical plates increase, your purity will also increase. A point to remember is that the lower curve is the bubble point, or up to the mark where you have evaporation. So think about this. Whenever you are looking at heating or evaporation, what is the first thing that pops in your head? A bubble. Similarly, when you cool your material, you see dewdrops kind of materials sliding down the apparatus. So the upper curve is the dew point and the lower curve is the bubble point. Below these, you have the liquid state. Above this, you have a gaseous state. Always remember, whenever you will evaporate, you will not go to the dew point. Otherwise, you will not be able to go anywhere on your graph, and you have to go towards the lower boiling component. If you go away from this, which is not possible, you would rather have a lower boiling material than the higher boiling material. So when you're reading this graph, be very careful. There are two kinds of questions that you can see on this. First, what is the boiling point of a given mixture? And second, what is the vapor composition of a given liquid composition. To answer your first question of what is the boiling point of a given mixture, let's say that I ask you to figure out the boiling point of 33% ethyl acetate and 66% butyl acetate. First, locate that on your y-axis and then evaporate it. The temperature of the bubble point curve is the temperature of your solution at which this particular composition boils. And so that takes care of our boiling point. So for example, in this particular case, what is the answer? So this is 100, this is 105, and this is 110. So our answer is somewhere between 105 and 110. So I'm just going to write it like 107 degrees Celsius. And you just have to choose the best possible option or write the best possible option. To answer our second question, what is the vapor composition of a given liquid composition? Again, your given liquid composition is, let's say, 33% ethyl acetate and 66% butyl acetate. You will evaporate it, you will cool it. Once you cool it, now you will see what is the corresponding composition. So you evaporate, you cool, and you observe what is the composition at this particular point. Now let's say that I see 45% ethyl acetate and 55% butyl acetate. So for the liquid composition, my vapor composition would be right here. While my liquid composition, the given liquid composition, is right here. There is a third type of distillation as well, which is known as the vacuum distillation. This is done for molecules or compounds which have very, very, very high boiling points. And so we are not going to focus at all on vacuum distillation. We will be doing and focusing more on fractional distillation. We will also be looking at the simple distillation when we do our qualitative 2 analysis.